I am now.
I was over there, so I didn't know.
It's okay. So you took your magnesium solid, you added it to your hydrochloric acid, and you produced magnesium chloride and H2 gas. Hey, if you were asked what type of reaction when you say this is, there's two right answers. Oh, we got them both at the exact same moment, a redox and a single replacement reaction. Well done. Proud of both of you. All right, now we need to balance the equation. So we need a 2 right here, and that is all. Now, it's extremely convenient when you have the thing given you and the thing you want have the same coefficient, because that will mean the moles are the same. You with me so far? So I would take my, I'll do it the long way, but 0.0225, I think is what I said, grams of Mg. Then I would have taken the molar mass of Mg, which was 24.3 grams of Mg per 1 mole Mg. Then this part you really don't need to do, and that's because this is a 1 and a 1, but you'll see. I'm just doing it the long way for clarity. Down here I need to get rid of mole of Mg, and there's 1. And I want moles of H2, and there's a 1. And that's how you would do it picket fence wise. Now, most of us have moved on from the picket fence, which is fine. You're like, hey, I'm going to just divide it by its molar mass. And since it's the same 1 and 1, I'm ready to roll. Okay, so that would have given us some moles. Someone type this in for me. That's not very much, right? Does that help, Carly? All right, then you would have plugged this into pvnrt. And we are solving for volume nRT over P, correct? Well, someone give me your temperature. 292. And our pressure, was it above or below 1? Okay, someone type that in for me. You got it, Seth? What'd you get? Oh, okay, never mind. Aisley's right about there. What'd you get? 0.022. And that would have been milliliters, right? Or sorry, that would have been liters. But we would have converted that to 22 milliliters. Then we could compare it. Okay, here's something kind of annoying about this lab. I have no idea why we're always so far off. I literally have zero idea. I didn't used to be this far off, but I definitely am now. What was your percent error, some of you? Yeah, it doesn't make any sense. We're not doing anything different than I did at the start of my career. I'm using the same magnesium, the same hydrochloric acid, the same tube, the same tap water. I don't get it. But we used to be within like 5%. And suddenly something's way wrong. I've thought like hours about it. I have no idea why it sucks. But, oh well. Anyone care? Okay.
How do we take the number that we got from like our 2? And how do we convert that into volume?
That is volume.
Oh, it is?
Yeah. That's the volume. It's measured in milliliters. Yep. So you either have to convert your math to milliliters, which I did here, or you have to convert your reading to liters and just 0.0 whatever your number was. Were all of your percent errors positive? Yeah, it makes no sense. I have no idea what's going on. No, that would change it like a half a milliliter. And we were off like 10. All right. Interesting. Why would they want to? Sorry, I'm just thinking out loud. Okay, moving on. Fair enough. I need to eat a cookie. And let's have you do a practice problem. It will take forever. These are hard. These are way hard. Are we ready? And yes, I'm literally making you do this so I can eat a cookie. Thank you. Yeah. And I've been on a diet. I've actually lost 7.5 pounds since Saturday.
Since Saturday?
Yeah. No, that's not healthy. It's not healthy. So since I know it's not healthy, I better eat a cookie and some 2% milk. All right, here we go. You can do this part and this part. Don't worry about this. And you can do this part. You will do this on the test. This is, yep.
That seems like a little bit hazardous.
So it's not. As long as you control it correctly, it's fine. Are you ready? Okay. How would you go about finding the total pressure inside the flask before the reaction when you have two different gases? It's not hard. Yeah, just add it. You find the moles of both and just add them. Doesn't matter that they're different things. Like in the air right now, we have nitrogen, oxygen, and a few other things. But like, it doesn't matter. Each one's independent. So you find the moles of each one of them and just add. Okay. So that's how you do it. How do you find the pressure at the end? This is the butt kicker. At the end, I have CH4 plus O2 goes to CO2 plus H2O. At the end, you're going to have some of this, and some of one of these. How do you find the total pressure of three gases at the end? Find their moles and add them together. Add them together and do it. So this is a limiting reactant and an excess reactant because the excess reactant has to be included. Seth, yes.
So like, I know you said about the before thing.
It's okay.
So, but why wouldn't we even have that process?
Why what?
So if it says, okay, great. So it says it's 23.76.
Oh, this you don't need yet. We have not gone over water vapor pressure. So just ignore that part of the problem. We'll explain it. It's coming up. Okay. First, I must microwave. What?
Why are you doing this?
Don't worry, I'll leave my mic on as I eat it.
Great.
Yep. It will be. Oh, I'm gonna microwave it. Hey, I finally put your grade in. I forgot, but yeah, good job. You're passing now. Ooh, I might need to sit after that. Wow. Yowzers. But like now that I got up, my head's lightheaded because my body's too busy breaking down complex carbohydrates. Oh, oh.
That's actual facts. That's actual facts.
What was the fact? I need to hear.
Like when you stand up too fast, it's because there's like a blood rush from your brain to your stomach, and so if you squeeze your stomach muscles, then it shoots the blood back up to you.
I feel better now.
And then you
Okay. So here we go, my friends. Are you ready? First, you got to balance this. If I remember, it's 1, 2, 1, 2. Is that right?
But we.
Okay, fair enough. Okay, total pressure inside the flask before the reaction begins. The only things inside this flask before it begins are oxygen and CH4. Fair enough. So in order to ever find any of this stuff, I got to convert things to moles, right? So I need the moles of O2 and I need the moles CH4. So to do that, I take their masses and I divide them by their molar masses. So it says 5 grams of each. So it's 5/32 for oxygen. Is everyone okay with that? Where I got the 32, O2 is, there's 2 O's, one's 16. And then methane is 16, right? All right. So what is 5 it is 5/16. So did I do this to myself? 0.156, which one's that one? 0.156, and what do I have over here? 202.
Huh? What? No. 0.313.
That's pretty close to 202. Everyone was off by 1. Okay, now I don't need to do limiting or anything right now. I just have to add them, right? So what's my total amount of moles now? 0.46 what? 9? Okay. And that's the moles of gas. Now, is it more than 1? Sure, but math doesn't care. That's the total number of moles. So now to find the total pressure, pressure equals nRT over V, correct? So I have 0.469, 0.0821, and the temperature says 25, which is really 298. That's the numerator, and then the volume it told you was 4. And what did you get, Payne? 2.86. Did you get that? Okay. And this is pressure, so it's ATM. Okay, so whether there's 1 gas or 20, we can find the pressure because we just add them together. You okay with that? All right. Then we skip this part. What is the total pressure in the flask at equilibrium? Okay, equilibrium just means at the end, and when it's returned to, it's 25 degrees Celsius. Okay, so now I have to do some chemistry. I need to know which one of these is my limiting reactant. And oh, good, I didn't do it because they're written in different orders. I thought there was no limiting reactant. Does anyone see why my mind thought that? But it's okay. So we look at this number, and that's your oxygen, right? And we ask ourselves, is 0.156 at least twice as much as 0.313? And since the answer is what? No, what's my limiting reactant? Oxygen, right? Everyone concur? Oxygen is my limiting reactant. So in my flask at the end, I'll have to draw it bigger here. I don't think I've ever drawn a symmetrical flask. It's kind of like trying to draw a star. The mask, oh boy. The flask at the end, we know it has water in it. We know it has carbon dioxide in it, and there's one other gas still left in it, and it is the excess methane, which is CH4. So I need to find the moles of each one. So I need to know the moles produced of water. I need to know the moles produced of CO2. And then I need to know the moles left over, okay, of the methane. I'm going to scroll higher, and I'm going to change it to red here. My limiting reactant moles were 0.156, correct? Which means, do you see there's a 2 here? It means this is also 0.156. Explain that to your partner, why those are the same value. Okay. Because they have the same coefficient, which means their moles will always be the exact same. Okay, so I'm going to come down here. I already know now that was water, wasn't it? 0.156. Okay, now looking and using the same logic, CO2 is 1/2 of what water is, right? Or 1/2 of what O2 is. So I take 0.156 and I divide it in half. Rebecca, I don't like your body language right now. Oh, okay. All right. Okay, 0.078. We can get that by knowing the moles of limiting reactant and applying their coefficients. Okay, here we go. This one is a little bit different. This stuff is used up, correct? And I use up 1/2 again as much of the limiting reactant. So I know I used, I'm going to put a minus here, 0.078 of CH4.
So you just minus that from
Right.
313.
So then I look at what I had to start, which was 0.313. And that will give me how much I have in excess. What?
0.235.
Okay, these are all moles. So what do I need to do with these now? I need to add them.
Funny too. It adds to the same number.
It adds to the same number by just crappy chance. So what was it?
0.469.
469. Now that never happens. It happened because I gave you equal grams of something that had half as much mass as the other, and the coefficients were a 1 and a 2. That doesn't happen very often. And you know what is stupid? I'll tell you in a second. All right, whatever. We plug that in, and guess what? The pressure is 2.86 or 7.
Yeah, I was slightly confused with that one.
Wait, wouldn't they all?
No.
They're not changing.
What's that?
If it's gas on both sides, moles aren't gonna change. It's not like they're being
The moles can definitely change. Mhm.
What do the X's look like?
You got it.
Like,
Matter can't be destroyed.
no, you're right. It is
I
not.
just confused myself.
But-
Like, they're the same answer. That's why.
All right. That was kind of annoying. Here's the deal. On the test, you'll do the other parts and they're not the same because there is not really this many moles of water that are gas. Most of the water is liquid. You okay with that? So that also makes it different. Okay, so this kind of will lead us into something we're doing a lot before this. Thanks for letting me eat my cookie. Nope. Thanks for not complaining that I ate my cookie. All right, so really today's goal is density and molar mass from pvnrt. It's more math. Who loves math? Almost all of you. I feel like I need to move to the back. I can't see. Oh, I almost tripped on my own chair. Oh no, that's why I came back, so I could see that Mr. Nelson is playing on his phone. Okay, I had a kid, he did pretty well in AP chemistry and he probably played PUBG or Fortnite 80% of the time in class. And he did okay. All right, here we go. A lot of this, if it doesn't make sense to you, don't stress about it. Just worry about the equation. Here we go. Densities of gases. It turns out if we divide both sides of the ideal gas equation by volume and by RT, we get N over V equals P over RT. Don't worry about this. You don't need this equation. You don't need this one. All right. So N is moles per volume. See this word right here? Oh, hey, I don't mean to highlight it. This word right here is density, right? Density is grams per milliliter, right? Or mass over volume, or not? Yeah. So we're close. How do we get moles and mass? Like, how do they relate to each other? The molar mass. Ooh, big brain. All right. So we know that moles times molar mass equals mass. So multiplying both sides by the molecular mass M gives this, where M over V is equal to P times the molar mass divided by RT. Or another way of saying that is density equals pressure times molar mass over R times T. I think I have it right here. Yeah, you can. Nope, I mean just the value from the periodic table. So if we were talking about oxygen, we'd say 32. Okay, this is an equation from pvnrt that has just been manipulated a little bit to solve for density. All right, so density equals PM over RT. So whatever. Note, one only needs to know the molecular mass, the pressure, and the temperature to calculate the density of a gas. So obviously I had a practice problem last year. Solve for the density given the molar mass of something, and I did CO2. All right, we have 20 degrees Celsius and 3.5 ATM. We won't do this. I have it on the screen already anyway, but you would just plug it in. I would take my pressure, which would be given, and that would go here. I would find the molar mass by adding the parts. CO2 is 12 plus 2 times 16 equals 44. That would go here. and then R is a constant, and then T would be given to you. So we would know that if I had these conditions, the density of my carbon dioxide would be 6.4 grams per liter. It's a pretty slick equation, but we don't use it very often. We use its twin, which is better. Not better, but it's asked more. It's right here. Hold on, it's coming up. Well, fine, we'll just do it here. If we rearrange this same equation, I just have molar mass isolated, it equals dRT over P. And this is the version that is tested 99% of the time. We're rarely asked for the density of something because we'll have the volume already and we can find the grams already in the problem typically. So what it will ask us to do is to identify what gas we're talking about. And we can identify that based on its molar mass. So this is the one that you really need to remember, not the other version. And it is that molar mass, as I say it, equals dirt P dRT over P. So here we go. Well, that's out of order. Here we go, here we go, here we go. So here we go. What is the density? This is not the version we use very often, but we can do it. We have density equals the pressure. 1.05, the molar mass of methane. You don't have it memorized, maybe you should by now probably for methane. That's CH4, which means it's 16, right? R, 0.0821. And T, it says it's at 298. And we end up with whatever that number is. What'd you get, Beal?
I got 0.66.
Now, my friends, density all year has been grams per milliliter, but the density of gases are grams per liter. They're not very dense, so they should be really small numbers. And that many grams in 1 liter, that's a pretty small number. Like water's density is 1,000 grams per liter. Okay, so these are just plug and chug given things. But usually we'll have a problem that's more in depth. A sample of 27 grams of a simple hydrocarbon is found to occupy 2.8 liters at a pressure of 3.4 atm and a temperature of 32 degrees Celsius. What is the molar mass of this substance? What is the most likely formula of this hydrocarbon? Draw the hydrocarbon. How many sigma bonds are in the hydrocarbon? And I could keep going. Like, what's its molecular geometry? What's its hybridization? Draw the Lewis structure. How many unpaired shares? And it could go on and on with just this same base. So here's what we would do. First off, the molar mass is equal to the density times R times T over P. How do you find the density? It doesn't give it to me. Mass over volume. So does it give us mass and volume? Yeah, it does. It has to, or this whole problem would fail. 27 grams is the mass. The volume is 2.8 liters. And is that 9.64? I did that in my head after I read Davis's calculator. 9.64 grams per liter. All right, now that's just the density, right? Now I got to plug it in to this. The molar mass is equal to the density, which is 9.64 times R, 0.821 times T, 32 is 290 Thank you. And I divide that by the pressure, which is, sorry, 305. That's why everyone was looking at me dumb. 305. 3.4. No, I screwed this part up, Davis. That's what they were saying. Okay. So I plug this in and M equals 71.0. Is that right? Okay. Now, all of you, you want exacts. This will never give you exacts, but it will give you close enoughs. Now, this is a little bit tricky here. This problem says it is a simple hydrocarbon. What that means is it is C's and H's with no double bonds. So I need to find a number that adds close to 71 that involves a ratio of C's and H's that meets this standard. So this is what I would typically do. I would divide this by 12. And what does that equal? Almost 6. So I'm going to guess this is a 5. Because I can't round up. 12 is the mass of carbon, correct? It's the most massive part of this. So I'm going to go C5. Now I have H's. If this is a simple carbon, I have no double bonds. So I have a C, a C, a C, a C, and a C. And then I would have to complete, and I would get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then I would ask myself, does this add up to roughly 71? It's 72, right? And that's good enough. Go ahead.
What, like, how much of a difference is
If this was the AP test, the math right here would have led to like 71.98. Like it would be really close if this is on the AP test.
Will you give us like multiple choice?
This would never be a multiple choice. It takes too much time. And you can't use a calculator with multiple choice. Okay, now let me walk you through my logic here one more time. We know the mass has to be around 71. We know that most of the mass comes from carbon in the compound. Carbon is 12. So you divide the mass by 12 and round down. And that's most likely what it will be, especially if it's a simple hydrocarbon, then it absolutely will be this. All right, then you draw the structure, complete everything with what it needs, and you're ready to roll. There is a cheat sheet, not a cheat sheet. There is a way to go about it. I don't know if I've ever talked about this. In a simple hydrocarbon, C will always have a number, and H will always be the number plus times, 2 times N plus 2. This is the formula for every simple hydrocarbon. So once I knew 5, I knew this number was going to be 12 because it was 2 times 5 plus that. You do not have to know that. So Brittany, don't make that kind of face. But you do have to be able to draw it out. Okay, sort of with me? This is a very, very typical problem on the AP test and on Tom Davidson's AP test. It will be a lot closer, so you're not like 1 or more off. It'll be close to what it should be. Okay, says we found the most likely formula. That was C5H12. Draw it. We drew it. How many sigma bonds are in the hydrocarbon? So that's every single bond, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Fair enough. There's all sorts of ways to apply this chapter to like everything we've ever done. And that's what AP likes. They like one question that can test multiple chapters. Right? Like I could literally test this question could be the stem for every single chapter we've done. Like we could light this on fire and it would give off light. And when it was analyzed, it gave off a light that was in the 460 nanometer range. We could find what its energy and wavelength and frequency were, right? Like every single thing we've done can be tested from chapter 10. I don't know if you guys were happy about that. Okay. I'm going to teach you something that's not on the AP test, but probably a third of you will go on in chemistry, and it's something that is useful. How much? I got 3 minutes. It won't be that bad. And that is this weird language of hydrocarbons. You can see I've been here before. A hydrocarbon is a combination of carbons and hydrogens. If it says it's a simple, it means no double bonds. So a simple hydrocarbon is called an alkane. In organic chemistry, there are alkanes. That means no, I think I have it right here, so I rewrite it. Alkane means there's not any multiple bonds. And the formula for alkanes are always CXH2X plus 2. They always are that. Now, there are substances in organic chemistry that are called alkenes. So ALKENE. Now, I didn't get to make these up. I know they're kind of too close to each other. In this language, we now do have a double bond. And in this formula, it would be CX and then H2X. We don't have the plus 2 because we now have the double bond, which removes a bond from each carbon because they're bonded to each other. All right. Then more rare are alkynes, YNE, and they are ones that have a triple bond. So that removes 4 total hydrogen bonds that could have happened. So now it's CXH2X minus 2. So we could have butane, butene, and butine, and they'd be similar, but different. They would all have 4 P's, but one would have all singles, one would have 1 double, one would have 1 triple. Now, you won't remember this, but I taught myself this forever ago. MEPB, then remember geometry. Meth, eth, prop, bute, and then geometry. Pentane, hexane, heptane, octane, nonane, decane. You've heard of one of those before. Have you heard of any of them? Propane heats your barbecue. Octane runs your car. Butane runs your camp stove or your crack pipes. And that's probably all you've heard of most of them. We just did one with 5. What would it have been then? Pentane. Okay. This is not on the AP test. It's not on my test, but you'll see it. You'll be like, hey, I remember Davidson taught me this in 3 minutes.